Okay, the second speaker this afternoon is Wouter Castryck. He's going to talk on the decision Diffie-Hellman problem for class group actions on oriented.
Okay, thank you very much. And also, for my part, thanks to the organizers for organizing this, one of the favorite conferences of many people in the audience, I think. So indeed, this paper is on the decisional Diffie-Hellman problem for class group actions on oriented elliptic curves. I will mention that at some point in the slides, but I want to stress that this is follow-up work of joint work with Jana Sopakova, who is in the audience. But okay, so we are discussing the oriented case, which is different from what we did in that joint work with Jana. Let me first recall what the decisional Diffie-Hellman problem is. So this goes back to the classical Diffie-Hellman key exchange protocol, and let me formulate it in the way that Diffie and Hellman did in 1976. So Alice and Bob, they agree on some prime P, and they work in the multiplicative group of the corresponding finite field. They fix a generated G, and Alice chooses a secret exponent A. My apologies, this is computer science notation, but this is the integers modulo -1. So Alice chooses the secret exponent A, raises G to the power A, sends it to Bob. Bob does the same, chooses the secret exponent B, raises G to the B, sends it to Alice. And now both parties can compute G to the A, B. For instance, Bob can compute it as the G to the A that he received from Alice raised to his secret exponent B. Yeah, and so this is then the candidate common secret for use in a symmetric key scheme, for instance. Now, ideally, if this would really be like a perfect situation, ideally an eavesdropper this secret is just random. So there is nothing special about this number. So let me formalize this in the decisional Diffie-Hellman problem. So this is a very important hard problem because it's like a security foundation for many security proofs. If you want to prove the security of a certain crypto system that is based on the discrete logarithm problem of the Diffie-Hellman problem, eventually you want to reduce to this decisional Diffie-Hellman problem, which is a stronger assumption. And so the decisional Diffie-Hellman problem is about playing the following game. So as an attacker, you get quadruples. And either these quadruples are consistently of this form, so they are really like the data of a Diffie-Hellman key exchange. So you see G to the A, G to the B, and G to the AB. Or consistently, the attacker gets tuples of the following form: G to the A, G to the B, and G to the C for just random A to C. Yeah, and the game he has to win is to decide from which of the two distributions the samples are coming. So this is the decisional Diffie-Hellman problem. And for the original setup of Diffie and Hellman, this is a very easy to break assumption because we have the Legendre. Okay, so yeah, if G to the A and G to the B are both squares, or even if one of them is square, then G to the AB has to be a square. And this is clearly not always true for a random field. Okay, so this Legendre symbol acts as a distinguisher. Of course, this is very easy to fix by working in some subgroup, and you want to do this for other reasons anyway. Okay. Now we are going to move to the class group action setting. So I will explain this notation throughout the talk, but let me already just show you the scheme. So eventually, Alice and Bob will agree on a certain set of elliptic curves. This will be the set of O-oriented elliptic curves over some algebraically closed field K. I will explain that. And there exists an action of the ideal class group of this O. What is O? O is just some imaginary quadratic order. So an order in imaginary quadratic field. Okay, so there's a natural action of this ideal class group on this set of elliptic curves. They agree on a base curve E, and now they play the same game. So Alice chooses a secret ideal class A, acts with this ideal class on this starting curve E, sends the result to Bob. Bob does the same, chooses a secret ideal class B, sends it to Alice. And eventually, both parties can compute the action of AB on. Okay, so for instance, Bob computes it as his secret ideal class, and he acts with it on the AE that he received from this. Okay, so the reason that we are interested in this is that this gives rise to potentially post-quantum alternatives to classical Diffie-Hellman key exchange, but I won't go into the details of that. But just here, so I recall K is an algebraically closed field. Of course, in practice, it will be some finite field. So you have to think of a subfield of K. O is this imaginary quadratic order. CLO is its ideal class group. This I will explain. So this is a set of O-oriented elliptic curves over K, and the action will be by means of isogenies. Okay, and then in this language, it's just the same thing. The game is to distinguish between quadruples of this form or quadruples of this form. And so the contribution we give is that we break this for almost all instances of the ideal class group. So we give a family of distinguishers, just like we had the Legendre symbol in the finite field case. And so these will break the decisional Diffie-Hellman assumption. And just like in the finite field case, it's very easy to counter this, take countermeasures. Okay, so here's a bit of a more precise statement. And because I'm mentioning complexity here, I'm immediately working over the algebraic closure of a finite field, but the method works over any field. Okay, so what we do is for every assigned character, so these are certain group homomorphisms from the ideal class group to this group with two elements. For every such assigned character, we show how to compute chi of A without knowing the secret ideal class state. So we are just given E and E prime. E prime is obtained from E by acting with the secret ideal class. So let me stress, this is unknown. Nevertheless, from E and E prime, we will be able to compute chi of A. And this is the complexity, but just remember that this is polynomial time in the field size, but it has its factor m to the 4, and m is the modulus of this character. I will get back to that in a second. Okay, and so this FQ, what is it? It's say it's the smallest field over which you can define E prime, and all these. Yeah, I will get back to these, but these will be endomorphisms on. So also M will become apparent, and I want to stress that this is a classical algorithm, although we are in this quantum context, and this is classical. And indeed, then this distinguishes, so this breaks the decisional Diffie-Hellman problem, at least as soon as this character is non-trivial, because that's not an assumption here. But if this character is really non-trivial, then about half of the cases you expect that chi of A times chi of B equals chi of C, and in half of the cases you expect that this is not true. But of course, you always have that chi of A times chi of B equals chi of A times. So this is then the distinguisher. And so very quickly, an attacker will be able to distinguish between these two distributions. Okay, so I will now go through a bunch of ingredients going into that statement. So first of all, these assigned characters, I will go quickly over them. This goes back to an old observation by Legendre, saying that if you have a divisor of the discriminant of your imaginary quadratic order, and now I will focus on odd prime because the prime 2 is a bit different. But if you have an odd prime divisor M of the discriminant, then this Legendre symbol, so you take the norm of a certain ideal, and you take its Legendre symbol over M. This Legendre symbol only depends on the class of the ideal. So it doesn't change if you take different representatives of the same class. Of course, you have to have this assumption that that's, every ideal class takes ideals satisfying this assumption. Okay, so in a different way, you can say that this is a well-defined map. You have you send the ideal class group to send an element of the ideal class group to plus or minus 1 by sending an ideal class to the norm of any representative, and it's I mean it's Legendre symbol. So this is the canonical example of an assigned character. I will not discuss these. I just included these for completeness. So also to the prime 2, you can attach an assigned character, but sometimes you have to attach 2, and sometimes you cannot attach any. So it's a bit different. We will not use this. These assigned characters, they relate to genus theory. So basically the number of assigned characters, this measures the size of the P portion. I will get back to that, but for the attack itself, we will not use that. Okay. What is also interesting that is at most one of these assigned characters is trivial. I said an assigned character could be trivial potentially, but this is only true for at most one. So if you play this game for 2 different assigned characters, you will definitely break decisional Diffie-Hellman. Okay, now about these oriented elliptic curves. So these are a bit of a hot topic recently in isogeny-based crypto. So what is an orientation on an elliptic curve? So again, we have our imaginary quadratic order O, and an orientation is simply an embedding of this imaginary quadratic order in the endomorphism ring. Okay, so of course, for this to exist, such an embedding, your endomorphism ring has to be big enough. I will give examples in a second. And we will always assume that our orientations are primitive. And this means that this O is the biggest possible. So you cannot replace O by a bigger order in the same imaginary quadratic field and still have such a. Okay, so that's a primitive orientation. And so here are some examples. You have a CM elliptic curve over C, or an ordinary elliptic curve over some finite field, or not a Vercauteren finite field. Then this iota, this embedding, will necessarily be an isomorphism. And so, in a sense, this is not super interesting in this case, although it's an important special case. But the more interesting special cases are the supersingular elliptic curves, because then this endomorphism ring is in order in a quaternion algebra, and you have many different imaginary quadratic orders living in there. So you have many different orientations. Okay, and so here I gave just a small example. If you look at this supersingular elliptic curve, so y squared equals x cubed plus x, in characteristic P, where P is 3 not 4, then, for instance, here you have two different orientations. So you could orient by this imaginary quadratic order by sending square root of minus P to the Frobenius endomorphism. But you also have an orientation by this imaginary quadratic order by sending square root of minus 1 to the automorphism. That's first. Okay. Now, if you have an isogeny between two elliptic curves, E and E prime, and if you have an orientation on your first elliptic curve, then this induces an orientation on the codomain curve. Okay. But if we talk about primitive orientations, then this orientation might be by a different order, but it will be in order in the same imaginary quadratic field. Okay. So given an O-oriented elliptic curve and an isogeny, you get a new orientation denoted by iota prime on E prime. It's an order in the same imaginary quadratic field, and the conductive changes by a factor which is at most degree of the isogeny. If we are in the special case where this O prime equals O, so where the ring doesn't change, then we call this isogeny horizontal. And this will be the only isogenies that we will be considering. As a trivial and maybe, well, as a special case, maybe a somewhat trivial case, if this is an isomorphism, and this is an isogeny of degree 1, so the conductor cannot change, and then you necessarily are in the horizontal setting, and then we say that the oriented elliptic curve E iota is isomorphic to the oriented elliptic curve E prime iota prime. The iota prime is this induced orientation. Yeah, and so this is this set LOK that was in the third slide or something. It's the set of all oriented elliptic curves up to isomorphism under this notion. This set is non-empty as soon as the characteristic of the field is not the divisor of the conductor of your imaginary quadratic. Okay, so bottom line, oriented elliptic curves are elliptic curves together with an embedding of this imaginary quadratic order O in their endomorphism. Okay, and then there's this class group action. As that this is an action by isogenies. This is also not very important. So let me immediately plot this and maybe also the next thing. So whenever you have an oriented elliptic curve, and whenever you have an invertible ideal I, then to this data you can attach an isogeny from E to another curve E prime, denoted by 5 subindex I. And the degree of that isogeny, sorry, there's an I missing here, is the norm of the ideal. And this isogeny is always horizontal. And so by this induced orientation, you get a new element of this LO. Okay. And so as it turns out, this pair up to isomorphism only depends on the ideal class and not so much on the ideal. And so you get a well-defined action. Well, that turns out to be an action. So you get a well-defined meaning of this, and it turns out to be a group action, and it's always a free group action, and it's usually almost transitive. But there are situations where you have to orbits. So that's why I didn't mention transitive. Okay, so this is the spool of oriented elliptic curves. I lost my laser pointer here. Yeah, spool of oriented elliptic curves. You have an oriented elliptic curve here. You act with an ideal class and you jump around. Okay, now what is the strategy for attacking decisional Diffie-Hellman? So an eavesdropper sees E iota and another oriented elliptic curve E prime iota prime, and he knows that this oriented elliptic curve is obtained from E iota by acting with some unknown ideal class phi. And so in terms of these assigned characters, the goal is to compute the Legendre symbol of the norm of I over M without knowing I. And the main idea is to use, okay, and so the inputs that he has is there exists an isogeny from E to E prime of this degree norm. And the main idea is to use pairings, and this goes back to this joint work with Jana. But here I formulated it in terms of the rail pairing. In the previous work we used the tape pairing. I will get back to that. But the strategy is really to extract information about this norm of I modulo M using the rail pairing. Okay, because the rail pairing satisfies this very nice property. So first of all, the rail pairing is something which is efficient to compute. And secondly, you have this property of the rail pairing. So that's the property that interests us. If you take the pairing of phi of P and phi of Q, then this is the same as the pairing of P and Q raised to the power of the degree of phi. And the degree of phi is this norm of I. So we kind of hope that we can use this identity. Of course, we don't know what phi is. We don't know what to put here. But the hope is that we can somehow exploit this identity to solve this problem. Okay, so here's the very naive version of this hope, and this will not work. So the naive version of this hope is just find matching point pairs. So PQ on the M torsion of E and P prime Q prime. So they should be generated because otherwise the pairing is trivial, but PQ in E and P prime Q prime. And imagine that we are lucky and that P prime is really phi of P and Q prime is really phi of Q. Yeah, then we can really compute these two pairings and we recover the norm modulo M as a discrete logarithm. But that's too naive. Okay, so this we cannot do. But here's an important relaxation. Instead of really wanting that P prime equals phi of P, it suffices that this is a scalar multiple of phi of P. For some unknown scalar, we don't need to know it. As long as our guess for Q prime then is related to phi of Q by the same scalar. Why is that sufficient? Why is that sufficient? Well, look at this identity. So this is an alternative version of this. So if we then compute the pairing of P prime and Q prime, in other words, if we compute this, then not only the degree of our isogeny phi comes out, but also this lambda comes out. But this lambda comes out squared. And we are only interested in the Legendre symbol of this norm. Okay, so it's sufficient to have this for some unknown lambda. Okay, and so this is really the strategy that we had in this previous work with Jana, and we could make it work for ordinary elliptic curves over finite fields. Okay, and why could we make it work there? Well, instead of the rail pairing, we used the Tate pairing, and the Tate pairing allows for non-trivial self pairings. So you can pair a point with itself, and the outcome is non-trivial. But that's very interesting if you want to have this same scalar lambda. Right? You just take some P prime, and you take Q prime equal P prime, and you take Q equal P, essentially. And you have this scalar lambda for free. Of course, you have to be a little bit less naive than that, but that's essentially the reason for resorting to the Tate pair, okay? Because you can take P and Q proportional. But to make this work, you need to have a cyclic and primary part. And for this, you need to go down to the floor of some isogeny volcano. And this is where the algorithm or the method crashes if you want to apply this to more general oriented elliptic curves, because in the general case, these isogeny volcanoes are infinite. So you don't walk to the floor. There's no point in walking to the floor of an isogeny volcano and make these groups cyclic. So the Tate pairing approach fails in the general setting, and this was actually the starting point of this research. We had an ad hoc solution for a very specific case, but also this ad hoc solution. How am I doing timelines? Okay, thank you. Okay, so we go back to the rail pairing. Tate has ruled out. Now, instead of using proportional points, we want to use points P and Q that are related through one of these isogenies or one of these endomorphisms that we get for free from the orientation. Okay. So what we do is we want to choose we want to select some well-chosen sigma in our O. To this sigma in O, we can attach an endomorphism, and we can use this. So this endomorphism is iota of sigma, and we can use this endomorphism to send P to another point. And we hope that this Q is independent of the initial point P, because then we already have a non-trivial well pairing between P and Q. Yeah, maybe. Okay, so maybe I should have put the formula here, but the end goal will be to consider pairings of the form E of P comma Q. So E of P comma iota sigma of P. Okay. Now here's the key observation. If we have if M is a divisor of the discriminant, then M is also a divisor of the characteristic of the discriminant of the characteristic polynomial of sigma. Okay, and so as a result, on the M torsion, iota of sigma has to have a double the characteristic polynomial has to have a double root, and this upper right entry here has to be non-zero if sigma is a generator. Because if it would be zero, then you can easily prove that this order has conductor at least M. Okay, so from this data, if sigma is a generator of O, and if M is a divisor of the discriminant, you know that iota of sigma has to act okay, with respect to some basis P1. Now, this P1 is not an interesting choice for us, and because P1 is an eigenvector of iota of sigma. And so if we would use P1, then iota of sigma of P1 would be a multiple of P1, and if we pair them, we would get something true, and we want something non-trivial. But P2 is a better choice, and because P2 under iota of sigma is mapped to alpha times P2 plus beta times P1. Yeah. And so we are going to concentrate on these non-eigenvectors. And the main thing that we can prove here, it's a little bit technical, so I hope it's well. If you want to ignore what I will print here, that's fine. We can go to the conclusion immediately. But the conclusion will be that if you take any non-eigenvector of iota of sigma and you pair that non-eigenvector with its image under iota of sigma, so you get a non-trivial value, then this value is basically up to squares in the exponent, but that's what we want, independent of the choice of this P. Yeah, and so here's the proof is a computation. I'm not sure if it's very interesting actually, so I hope you believe me. So I will just go over this. It's just a computation using properties of the well pairing, but I'll jump to the conclusion. That's fine. Yeah. So so based on this input, you can show that this value up to squares in the exponent is independent of the choice of P, as long as P is a non-eigenvector. And so in a sense, you could say that this thing here up to squares in the exponent, this class, so you can put squares in the exponent, this is an invariant of your O-oriented. Okay. So then this is the method. What we do is we pick a generator of O. We also pick it of norm co-prime with M. I will explain in a second why we need that. But just let me stress that this is very easy to find in practice. Yeah, sigma doesn't work. You can take sigma plus 1 or sigma plus 2, and very quickly you will have one of norm co-prime. We also take a non-eigenvector P of iota of sigma. We take a non-eigenvector P prime of iota prime of sigma. Now these two here, this is the reason for this norm co-prime to M thing, ensures that phi of P, so even though we don't know phi, you know that phi of P will be a non-eigenvector of iota prime of sigma. This is where we use that the norm is co-prime to M. And so now we have this, we are in the setting of the previous slide, right? So we have a non-eigenvector P prime, we have a non-eigenvector phi of P, so we know that these corresponding pairing values are completely related up to the square in the exponent. So this is this expression. Okay, so this is something we can compute, and we know that this thing that we can compute is just this thing up to the square in the exponent. But now we use this compatibility property of the Weyl pairing. We can take this phi out, and we get this. And And so we can recover the norm of I modulo m by the speed of the computation. So this is the method for odd m. So it's actually quite simple. It's actually simpler than what we did before, although it's a little bit slower. I will say something about that. For even m, it's more technical, but it also works. So you have to be a little bit more careful, but it's in selecting this piece. But in the end, it's not complexity-wise. It's not, definitely not more difficult. Okay. So here are a few remarks. So if we we can apply this to arbitrary oriented elliptic curves. So in particular, we can apply it to ordinary elliptic curves over finite fields, and then we can compare with the previous methods. And it's definitely simpler conceptually because there's no descent of the isogeny volcano is needed. You don't need to talk about all these volcanoes. Although behind the proofs you can see them at work sometimes, but conceptually definitely simpler. But in the worst case, it's slightly less efficient. And the reason is that for the Weil pairing, you need to see the full torsion. So you need to go to an extension field where you see the full M torsion. Whereas for the Tate pairing, you only need one component. And so you can sometimes work over a small extension. Okay. Now, in the previous slides, we always focused on one character. But imagine you can play this game for all the assigned characters. And what you basically do is you compute the cosets of the secret ideal class A modulo squares in the ideal class B. Okay. Now the likeliness that you can do this is not very high because remember the complexity of this attack is O of m to the 4, where m is the modulus, so m is the size of the device. Okay. So if this m is big, you will not be able to carry out stuff. But in some cases, you will be able to do. Yeah, and then you can, but this is just purely pure speculation. So we don't have any ideas how to generalize this to, for instance, from quadratic characters to higher characters, or to determine the coset instead of modulo squares, modulo 4 powers or 8 powers. But these seem to be the most likely candidates for success because there is some, at least on the class group side, there is some theory about that. For 4 and 8, you have these Reday matrices, and then for arbitrary power of 2, you have recent work by Smith, but I don't know anything about that. So maybe this is nonsense. Okay, so to conclude, yeah, okay. So to conclude, I want to show an application. So here's another problem. Besides the decisional Diffie-Hellman problem, you can ask for something much stronger to an attacker. Namely, an attacker sees E and E prime, and E prime is obtained from E by acting with A. And so the attacker's task is to find A itself. Okay, that's of course much stronger. So this is the vectorization problem, and this, yeah, if this gets broken, then we are really in trouble. The decisional thing you can take out the measures for it, but here we will really be in trouble. And so people have, because yeah, in isogeny-based crypto, the endomorphism ring computation problem is often considered like as the most fundamental problem. And people are often interested in relating the hardness of other problems to the hardness of this endomorphism ring computation. And so this is a theorem from early this year by Wesolowski. And he showed that if you can compute endomorphism rings of supersingular elliptic curves over, so he's focusing purely on the supersingular case, then you can indeed solve the vectorization problem in a time which is polynomial in log p, but also polynomial in the size of the two torsion part of it. And this is potentially very big. And so in the cases where this is very big, this is not another very useful reduction. For instance, the worst cases are where your discriminant is like a product, like you just take the first so many primes and you take the product of all of them. This is the primordial case. In that case, you will have a very big size of the class group, and this will be actually an exponential reduction, so a meaningless reduction. And the source of this term here is that the reduction does not compute A directly, but it computes A squared. Okay, and this is like a technical artifact of this reduction. And so to go from A squared to A, what Wesolowski does is just he does an exhaustive search through all these elements of order 2 to find Yeah. But of course, if we can compute A modulo the square of the class group using our methods, then we can avoid this, can completely avoid this exhaustive search. So we will solve it completely. Okay, so this is like the good news. However, one has to be careful because in general, as I said, we don't compute this class in polynomial time. Our complexity really depends on the size of this M that we are considering. So for small m, we can compute this efficiently, but for large m, we can't. But luckily, or interestingly, maybe the best situation would even be a bit better than we have now. But interestingly, the worst cases for this exhaustive search, like this primordial case, they are the best cases for our attack. Yeah, because in the primordial case, when you have many, many prime factors, then necessarily all these prime factors are small. And so we can run our attack. And so the worst cases for exhaustive search are our best cases. And so you can make a trade-off, and this lands in the sub-exponential. So this is, so the worst case reduction now dropped from exponential time reduction to a sub-exponential time reduction. So that's an application of this, I'll stop here.